structural basis for anion conduction in the calcium activated chloride channel TMEM16A. This paper is written by Christina Paulino, Yono Nedler, Andy K.M. Lam, Valeria Kalinokova, Janine Denise, Brunner, Stephen Sneck, and Raymond Dassler. This paper is published in the Journal of eLife and is published in May 2017 by the Department of Biochemistry, University of Zurich, Switzerland. Calcium activated chloride channels. Calcium activated chloride channels are ligand-gated ion channels. As the concentration of the intracellular calcium ion increases, it results in the activation of the calcium activated chloride channels. These are mediated by the protein TMEM16A. TMEM16A is a member of conserved TMEM16 family of membrane proteins. These membrane proteins are also known as anectomines. Initially, it was thought that all the TMEM16 proteins they function as anion channels, but later they realized that only TMEM16A and TMEM16B work as anion channels. Other members of the family they work as lipid scramblerases. In general, TMEM16 family proteins are homodimers, and each subunit has its own translocation pathway. In a fungus, NHTMEM16 is found, which is a fungal homolog. In fungi, this lipid pathway is also formed by a subunit cavity. This subunit cavity it spans around the membrane and is large enough to harbor a lipid head group. Near to each subunit there is a furrow in which the conserved regulatory calcium binding site is present. Although the structure of scramblerases NHTMEM16 has defined architecture, yet it is unknown how TMEM16 function as anion channels. So the scientists in this experiment have tried to address this issue by the structure determination of mouse TMEM16. The electron density map it identified and showed the main features of these membrane proteins. Because of the structural similarity of NHTMEM16 and TMEM16A, polyalanine model was established. This model included the secondary structure as well as the elements of the transmembrane domain along with C-terminal and N-terminal cytoplasmic domains. The above figure represents the ribbon structure of the mouse TMEM16A. Here the dimers are superimposed on the fungal homolog, that is NHTMEM16A. The overall structure of mouse TMEM16A and NHTMEM16 are very similar. Of TMEM16A were clearly resolved using cryo-electron microscopy and are very similar to TMEM16 counterpart. The figure A suggests there is an unassigned density on the extracellular side. Extended loops which join the transmembrane alpha helices 1 and 2 and transmembrane alpha helices 9 and 10. These extensions they eventually turn into a compact extracellular domain which in turn has 6 residues. These 16 residues are very important for the channel activity. Figure B shows the structure of the N-terminal domain. N-terminal domain has 92 residues longer than its counterpart TM-EM16, whereas C-terminal domain is 38 residues shorter. Figure C. Figure C shows the ribbon presentation of the mouse TM-EM16A, and it represents the N-terminal domain as well as the C-terminal domain. Figure D. Figure D suggests that the alpha helix number 10 of the transmembrane domain and alpha helix number 1 of the C-terminal domain of both the subunits are imposed on the fungal homologue NHTM EM6 because of the similar location of the subunits in NHTM EM16. Now the above video is about the pore region which possesses the calcium binding site. This calcium binding site is formed by transmembrane alpha helices 3 to 8. The video is a superimposed image of TM-EM16 channels and scramblices NHTM-EM16 are shown. Blue represents the helices of TM-EM16A, whereas beige represents the fungal homologue NHTM-EM16. Calcium ions which are bound are represented by green. From this study, it is determined that the protein contains 2 ion conducting pores. These pores are independently activated by calcium ions. These pores are located within each subunit of the dimeric proteins. The positive charged ions are represented by blue and the negative charged ions are represented by green. The ion conduction path in TM-EM16A consists of a funnel-shaped intracellular vestibule. This vestibule narrows down to a tight pore at the extracellular part of the membrane. After shedding their hydration shell, the permeating ions interact with the pore lining residues, thus facilitating their transfer. The next figure shows the rearrangement of the alpha helices. The first figure A suggests the arrangement of the alpha helices in the scramblase. However, the rearrangement results in the formation of a channel that acts as a calcium activated chloride channel. This rearrangement of the alpha helices results in the blocking of the lipid pathway and opening of the conductive pore. Thus, this study reveals the structural relationship between scramblases and the ion channel in mouse TM-EM16A, where a hydrophilic membrane exposed cavity in scramblases has turned out to be an ion conducting channel in structurally related mouse TM-EM16A. Thank you.